Hello, this is Eric from UNC Charlotte, and this is part 5 of our C++ crash course. Once again, this C++ crash course is not meant to teach you all the C++ that there is to know. It is mostly meant to catch people up that know how to program in other programming languages in how typically C++ gets programmed in practice. After a part 1 on types and a part 2 on objects, we had a part 3 on functional programming and a part 4 on how to deal with C-style programming. What we will do today is to look at how C++ gets compiled, and we see that how C++ applications get compiled is rooted in how C applications were compiled at the time. There were changes that were made recently in the C++ standard in C++ 20 to how C++ will get compiled in the future, and that should simplify a lot of the things that I will present today. But they're still fairly recent, and therefore I'm not sure they are worth mentioning at this point. All right, let's look at how it works. Here we have a simple toy application. We have 3 files. At the bottom we have main.cpp, and let's look at how it works. So main is going to call a function f, and it's going to create an object a and call the g function on it. You can see that these things are not actually included in this file. There is no definition of what f is, there is no definition of what the type a is, and there is no definition of what that function g is either. Main is going to know what those things are because main is going to include that file helper.h, and helper.h is the file that will actually define what these things are, what these symbols are. And you can see that it defined function f, but it doesn't actually give the body of function f. It also defined a struct a, and it says that yes, there is a function g in it, but it doesn't actually say what that function g is doing. There is a third file called helper.cpp, which is going to actually provide those function f and that member function g for object a, and these are correct notations. Whenever we run this application, we'll have to compile it first. So usually you compile it with make, and you can see what make is doing. Make is actually calling the compiler multiple times. It's first calling the compiler to compile main.cpp, then it's going to compile helper.cpp. Whenever it does those things, it's going to create 2 files, which are .o file, they're object file. They are intermediary file in the creation of your application. And then it's going to call G++ again in order to merge these 2 object files into an actual binary, and then we will be able to run that binary. These are the 2 steps that you will always see whenever compiling a C++ application. You'll have a step which is called compilation, and you have a second step which is called linking. And understanding the differences between those 2 steps is important because it can help you debug why your application does not generate. Most of the time people call that the compilation process. When you say you need to compile your application, that usually means you need to create object file and then do the linking. But when you start looking like down the guts of how the compilation process goes, you have an actual phase of compilation, which is going to transform your code files into object files, and then a phase of linkage, of link addition, where they will transform object file into a binary. And you can see that happens because make knows what to do. And if you're wondering how make knows what to do, it's because this particular project comes with a Makefile, and that Makefile is going to detail how the things need to be compiled. It will show you how to compile main, and you can see that there are actually variables that can help you parameterize how that compilation process works. And roughly the syntax of the thing is that main is going to depend on these objects, on main.o and helper.o. And once you have these objects built, then you'll be able to build your binary by using this recipe. The syntax of Makefiles can be a little bit obscure. I don't want to cover what it is, but I want you to understand that typically you have some kind of a build mechanism that will actually build the application for you. Here I'm using Make and Makefiles. People are going to use like project in Visual Studio or whatever. But there is always some kind of a tool chain on the back end that will actually build your application. And we can try to see what happens if we don't actually specify the files correctly. If we try to build things incorrectly, here I have a target in my Makefile called make incorrect. And let's see what happens. Whenever we try to create it, to build main incorrect, you can see what's happening is that we try to compile, but we actually only pass one of the .o file. We didn't pass both .o file. And so that means that we're going to get an error that is a linker error. And you can see here that what we have are actually linker errors. There are multiple ways you can tell that this is a linker error. The first one is that it has already built main.o. That means that main.o compiled correctly. But what you get is the problem that you're getting is that there is an undefined reference to a function. So that means that whenever you compiled, the compiler knew that there is a function f that exists, despite he didn't have the body of that function available. But when he tried to link, he couldn't actually find f. So that means that it's going to be a linking error. There is another way you can tell here that it's a linking error because it uses the binary LD, and LD is the linker of the GCC toolchain. And so that's how you know that these are linking errors. These are not compilation errors. These are linking error because the files compile, the CPP files compile correctly into an object file. But the object file could not be transformed into a binary because there were missing functions. So this is typically how C++ projects are going to be structured. Most of the codes themselves are going to be given in CPP files, and we're going to have other files, header files, which are usually .h file or .hpp file or something like this, that are going to be used to define the interface between those different object files. And this is what that header file does. I want to attract your attention on these pound ifndef and pound define and endif that you find here. These are actually C preprocessor style macros that are going to control how things get compiled. And that ifndef, it's if that particular symbol is not defined, then you execute that if, and the first thing it does is define it. This is a construct that you see all the time in C and C++, and the goal of having these lines and the endif at the end is to make sure that the same header file does not get included twice, because if you included it twice, then that means that you would declare function f twice, and that would cause a compilation error. If you're wondering how that process works of actually using those header files, this is actually a pre-processing stage in the compiler that actually comes before the compiler itself. You can actually see it by passing extra parameters to G++. If you pass parameter -E to G++, then the compiler G++ is going to stop the compilation process after pre-processing, which means that it's going to generate an actual CPP file. And we can see what that file is going to look like. That's the compilation of that helper.cpp file, and you can see that it does include iostream and it does include helper.h. And you can see the output of that process, and the output of that process is long. The reason why the output of that process is long is because that pound include is essentially doing a copy and pasting of that file iostream into the code, and then it's going to go ahead and copy paste helper.h into that code. That's why you end up having that very, very long code here, because iostream is a fairly large it's a fairly large file. And so if you're going at the end of it, which for some reason it's not letting me do, there you go. If you go at the end of that file, you can see that you actually have the content of helper.cpp that is in there, and you do have the content of helper.h that is in there, because those files were essentially copied inside helper.cpp, or actually they were assembled during the pre-processing stage. And that's why you can have errors like if you include the same header file multiple times, then that piece of code would actually appear twice. If you were not to include that file here, you would actually not be able to compile main. Whenever you would try to compile, you would actually get a compilation error, and you can see that this is a compilation error and not a linking error, because the line that fails is the line that tries to construct main.o out of main.cpp. And the type of errors that you get are errors of compilation. They're not errors of linking. What it tells you is that f was not declared in the scope. So it means that whenever it tries to compile this line, f was not a symbol that was known. There is no f that is defined anywhere. And it's not defined because we commented that helper.h line. Similarly, it couldn't find what a is, and it couldn't find what small a is. Like, it was not declared in that scope because it didn't find what big A is, so it didn't understand it was a variable declaration. So understanding how applications get built in your language is going to help you identify errors in your code. And you can actually stop the compilation process at different stages of the process. In a typical compiler, what happens is that it takes the CPP file. First, it will apply some pre-processing to resolve all these pound includes and all those preprocessor directives. Then it will get an actual complete CPP file with no preprocessor. Then it will compile that down to assembly, and you can actually see that process as well. There is typically a parameter to the compiler in G++ is -S that allows you to do that, where you can see what your code looks like after compilation. So this is assembly code. Then it's going to generate the actual object file. That is the binary version of the assembly code that is properly decorated so that linking can work. And finally, it's going to create the final binary. This style of modular compilation is old. It's very old. It dates back from the original days of C. And C++ is trying to change that to systems that are a little bit more modern. You don't have to deal with those crazy header files, for instance, in language like Java or D or Python. And that system is very archaic and can cause lots of strange compilation errors. So modern C++ is going to introduce a new feature called modules. They were actually voted on by the C++ committee for C++20. But C++20 is very recent at this point, so I don't want to talk about it too much. But hopefully modules, when they come, are going to make our life much, much simpler to deal with complex application. All right, that's the end of this part of this C++ crash course. And the next part will be about debugging C++ applications. Goodbye.